Well, this session will give the details of the efficiencies of different commonly seen mechanical and electrical devices. The first term is called the mechanical efficiency. This one is the mechanical efficiency, which used to describe the performance of devices that's used to convert mechanical energy to another mechanical energy. Okay? For example, an electric motor supplies shaft work to a fan to motorize the fluid. If there are no energy losses, all of the shaft work can be converted to the mechanical energy supplied to the fluid. Therefore, the mechanical efficiency is given by this one. That is mechanical energy output divided by the mechanical energy input. And sometimes we can write it to be 1 minus the mechanical energy loss divided by the mechanical energy input. Okay? Here is a little example on how to calculate the mechanical efficiency of a fan. Okay? Here we can see that suppose V1 is 0 and V2 is 12 meters per second. That means originally at this position there would be no kinetic energy. But of course, there should be some kinetic energy so that it can get into this fan. But we set to 0 so that we can get the KE. Okay? And V2 is 12 meters per second. And the elevation are the same and the pressure are the same so that we can find out the efficiency of a fan. It will be equal to delta E of the fluid divided by the shaft work. And the shaft work is 50 watts, we have given that. And the change in the mechanical energy of fluid is just the change of KE. Okay, we have neglected all other kinds of a change in the mechanical energy. Okay, so we just have this mass flow rate times V squared over 2, and we plug in values and find that it will be equal to 0.72. That is 72%. That will be the pump efficiency. Well, here you can see that we will use different kind of devices to increase the mechanical energy of the fluid for different purposes. For example, we would like to increase the velocity of fluid, increase the pressure, or bring the fluid to a higher elevation. Okay? Well, this is done by devices like pumps, fans, and compressors. Well, here we group all of them together as pumps. The different purposes of those devices will be further discussed in chapter 5. Okay? So if you don't understand what's the difference between a pump and a fan, just ignore it at this stage. We will talk about that in chapter 5. Okay? Well, the pump efficiency is given by the mechanical energy increase of the fluid, because that's the mechanical energy output from this pump divided by the mechanical energy input. And this mechanical energy is given by the shaft. So we have a W dot shaft in. Okay, so this delta E, okay, this delta E is equal to the W dot of the useful power of the pump. Okay, U means useful. Okay, that's the useful power of the pump. And after that, we will talk about the turbine efficiency. Turbine is a device that's used to extract mechanical energy from a flowing fluid, and the mechanical power is produced in the form of a shaft work to drive the generator or other rotary devices. Okay, here you can see that, well, the turbine is just the reverse of the pump. Okay, for pump, we input some shaft work to increase the mechanical energy of fluid, while for turbine, we will extract some of the mechanical energy inside the fluid to turn the shaft. So that this turbine efficiency will be defined as this one. So mechanical energy decrease of fluid is a denominator. The numerator is the mechanical energy output. This is the useful output, while this one is the input. So this one will be delta E dot of the mechanical energy of this fluid. We have put an absolute sign here because it's a decrease, so that if we calculate this delta, it will become negative. Okay, so we need to add a absolute sign here. For the numerator, it will be equal to the shaft work output. Okay, well, it will be equal to the power extracted from the turbine. Okay, that's the denominator. The numerator is the power delivered by this turbine. Okay. Sometimes we will also talk about the second law efficiency. Well, what's this? Well, as you can see, this efficiency, we just use the quantity of the energy to define efficiency. But later we will see that no actual devices can achieve 100% efficiency if we use this kind of efficiency to define. Okay? For example, for heat engine, it's used to turn the heat into work. Okay? In terms of quality, the quality of heat is much worse than work, so that it cannot convert all of the heat into 100% work, so that it will have a cap on the efficiency. In order to deal with this problem and express the efficiency in a better way, we will define what we call the second law efficiency. That's the absolute efficiency divided by the maximum efficiency. The absolute efficiency is talking about the efficiency of this actual device divided by the maximum efficiency that can be achieved by using reversible devices. Okay, we will talk about this kind of concepts in chapter 6 and chapter 7 when we talk about the second law of thermodynamics. But for the actual discussion of the second law efficiency, please refer to McCann 3300. After that, we will talk about the efficiency of some electrical devices instead of some mechanical devices. Okay? Pay special attention to these two kinds of efficiency. They are not mechanical efficiency, but they are efficiency defined for the electrical devices. Motors and generators are commonly used electrical devices. Motors are used to convert electrical energy to the rotational mechanical energy, while the generator converts this rotational kinetic energy to electricity. As a result, the motor efficiency as a generator efficiency, we also use what we have for the efficiency to define this one. The eta of the motor, okay, well, this Greek letter is read as eta, okay, eta. Eta of motor is equal to mechanical power output divided by the electric power input, okay? Or you can write that to be the shaft work output divided by the electrical power input, okay? For generator efficiency, it will be exactly the reverse, okay? That is the electrical power output divided by the shaft power input, okay? Well, as a pump usually works on a motor and a turbine usually works with a generator, we also have this kind of a combined efficiency. That is, we coupled the pump and the motor together to get this efficiency. That's the pump motor efficiency. Okay? Well, as I've said that, if we can divide a big process into a sequence of process, then overall efficiency is equal to the products of the individual efficiencies of individual processes. So that it will become what? It will become the electrical input as a denominator. The useful pumping power would be the numerator. Okay, and for this combined efficiency, okay, we will write it to be the turbine gen. Okay, turbine gen means the combined efficiency. Again, it can be divided into two efficiencies multiplying together. It will be equal to electrical power out divided by the turbine power extracted. Okay, so here it will be an example of this turbine generator devices. So you can see that how can we find out the efficiency? Well, we have the turbine efficiency, 0.75, as well as the generator efficiency, so that we can multiply it to get the combined efficiency. Okay? Well, as I've said that, the definition of efficiency introduced in this chapter is based on the quantity of energy. Okay? Thus, it will impose some misunderstanding on it as we have ignored the consideration of the quality of the energy. Well, there's a cap of efficiency below 100%, even though we try our best to improve the efficiency. Okay? Even for the best devices, we cannot get to 100% efficiency. This is governed by the second law of thermodynamics. Therefore, we will define a new term called the second law efficiency to reflect the actual performance of a process, which is the actual efficiency of a process divided by the maximum efficiency one can achieve in that process. Okay? Well, the concept of second law will be discussed in chapter 6 as I mentioned, and if you would like to know more about this second law efficiency, please refer to McCann 3300. Okay? Below will be two examples showing the problem that we will encounter in the real-life applications.